In our previous session, we had discussed about the fundamental equations. Now let us start off with drag. Wing creates lift due to the combination of fundamental principles of aerodynamics. When two masses are in contact, they resist each other's motion. In the case of an aeroplane, air resists the forward motion of aeroplane. So when it comes to flying, drag is resistance of an aircraft's movement through air. Total drag comes from different types of drags. The classification will be seen next. Drag is a force that resists the movement of aircraft through air. Let us see the different classifications of drag. There are basically different types of drags. We have drag, which is classified into induced drag, parasitic drag, and parasitic drag classified into interference drag and profile drag. And profile drag is classified into form drag and skin friction drag. Parasitic drag. Parasitic drag is simply caused by the aircraft's shape, construction type, and material. For instance, an airplane with a rough surface creates more parasitic drag than the one with a smooth surface. There are basically three types of parasitic drag. Skin friction drag is the result of the aircraft's surface being rough. Swimmers usually use swim caps on their head so hair doesn't create extra drag and they can swim faster through water. This same principle can be applied to the most aircraft where a smooth skin reduces skin friction drag, improving performance or fuel efficiency. Foam drag is the result of an object's general shape in relation to the relative wind. Have you ever stuck your hand out of the window of a running car? First tilting it flat and then vertical into the wind, you might notice how when your hand is horizontal like an airfoil, that little effort is required to stick it out. But when you open your hand into the wind, your hand has a tendency to fly backwards and requires more force to hold in position. This is the easiest way to understand foam drag. Then we have interference drag, which is generated by the mixing of airflow streamlines between airframe components such as the wing and the fuselage or the landing gear strut and the fuselage. As air flows around different aircraft components and mixes, a localized shock wave is formed, creating a drag sum greater than the drag that components would be having by themselves. For instance, look at where the fuselage and the wing meet. Interference drag forms behind the trailing edge of the wing adjacent to the fuselage. Airflow over top and underneath the wing mixes with airflow around the fuselage, creating interference drag. Now we have induced drag. Induced drag is created as a result of lift. As your wing passes through the air, an area of lower air pressure is formed on the top of the wing. Higher pressure air below the wing seeks equilibrium with the lower pressure area above, resulting in vortex flow from the bottom of the wing. These vortices change the direction and speed of airflow behind the trailing edge of the wing. The airflow deflects downward, which is called downwash. First, you need to understand the difference between an airfoil and a wing. An airfoil is idealized two-dimensional slice of a wing and it is analyzed with two-dimensional flow. For an airfoil, lift is up and drag is in the direction opposite to the direction of travel. The airfoil is designed to accelerate air, thus creating the pressure differentials that make the plane fly. The higher the pressure areas will try to push the wing towards the lower pressure area. The overall sum of these forces are called the resultant force. A perfect airfoil would create a vector pointing directly upward 180 degrees from the ground and 90 degrees from the direction of travel. The 90 degrees from the direction of travel is called lift and the remaining part, which is 180 from the direction of travel, is called the induced drag. Since it is induced by the creation of lift, even a wing producing lift at zero angle of attack will still produce a certain amount of induced drag. A wing is producing lift. It will also produce some induced drag. As you increase the angle of attack, the vector of the resultant force tilts back with it. Not necessarily at exactly the same rate, but usually not far off. Since we are still defining lift as 90 degrees from the direction of travel and drag as 180 degrees from it, the ratio between the two changes. For every bit of lift produced, there is a lot more drag and further you tilt the wing back. Induced drag produces vortices in circular patterns of rotating airlift behind a wing as it generates lift. Real planes have wings which are three-dimensional and have a finite span, a tip-to-tip length of the wing. For a plane to fly, the pressure under the wing must be greater than the pressure over the wing, and the net resultant is the lift. The wing behaves like an airfoil until you get near the tip of the wing and where there is three-dimensional flow. More simply said, the pressure difference causes flow to go from under the wing to over the wing at the wingtip. This spillage causes vortices to form at the tip of the wing, and the rotation direction is such that the flow behind the wing is driven downward by the two vortices, of which forms a wingtip. The net resultant is the lift force is no longer straight up. It gets tipped back slightly, and that means some of the lift now becomes drag. This is induced drag or drag due to lift, and it always happens for three-dimensional wings. These are few of the airfoil wings and their vertices. Finally, this is how a vertex looks in designing. This is NACA 23012, NACA 0012, NACA 2412 airfoil. I hope you would have understood today's session about drag. Thank you.